Good morning, good afternoon. Thank you for inviting me to give this talk to the ICTMUS conference. My name's Adrian Matthews from the University of East Anglia in the UK, and I'm going to talk on propagation and growth mechanisms for convectively coupled equatorial Kelvin waves, or CCKWs. So many of you are familiar with CCKWs. They're eastward propagating weather systems in the tropics. I'm going to use the method of Baranowski et al. 2016 to identify them, and I'll be showing diagnostics based on a base point in the equatorial Indian Ocean shown by the green dot here and in many of the later figures. So what I've got here are lagged composites of trim precipitation anomalies relative to this base point, and you can see the top panels at lag -1 day, then 0 day, and then 1 day. And what you can see is a nice clean eastward propagation of a positive precipitation anomaly of about 10 meters per second, and that's basically a CCKW. CCKWs are important. They occur throughout the tropics. They bring extreme precipitation to the maritime continent and elsewhere, and they're also a component of the Madden-Julian oscillation. So what we're going to address here is how do CCKWs actually propagate eastward? Is it the same mechanism as the theoretical equatorial Kelvin wave, or are there additional mechanisms as well? And also, how do CCKWs grow? Because the theoretical waves are neutral, they have no growth. So we're going to approach this using the vorticity equation, which you can apply to the dynamical fields, the wind fields, at a single level. So I've got the vorticity equation here in all its glory. On the left-hand side, we have the vorticity tendency, the rate of change with time of vorticity, zeta. And on the right-hand side, we have a sum of lots of different source terms. So looking at those source terms individually now, the first three in red are advection of relative vorticity, horizontal and vertical. The next two terms in blue are from vortex stretching, and this is from the divergence acting on F, the Coriolis parameter, and also on zeta, the vorticity in the wave itself. Then we have the minus beta v term, the advection of planetary vorticity term. That's the Rossby wave mechanism. And then finally, we have these so-called tilting and twisting terms, where you can take a vortex that's in the horizontal, and the wind can tilt it or twist it into the vertical. And then finally, there's this epsilon at the end, which I've allowed. That's the residual, okay, so any imbalance in the equation. So that's due to errors in the system, but also it's due to any subgrid scale processes that we won't be able to resolve. And I should point out here that this vorticity equation is much simplified for a theoretical Kelvin wave. The only non-zero vorticity source term is the minus FD. All the other terms for a theoretical wave are zero, so it's a relatively simple balance. So if we look at a theoretical Kelvin wave, here's the dynamical structure of one. So you can see I've got wind vectors plotted here. They're all in the east-west direction. There's no V wind. They're a maximum at the equator, and they decay north and south with a Gaussian structure. And then that leads to, in this case here, a cyclonic vorticity pair. So the vorticity is shown by colour shading here. We have positive to the north and negative to the south. They're both cyclonic. And then the other key feature here is the blue dashed lines, which show the region of convergence between the westerlies here and the easterlies there. So we can use this to look at how a theoretical Kelvin wave propagates. So on the next slide, the line contours here are the vorticity anomaly that was shaded in the previous slide. And the shading, so again, we've got that cyclonic vorticity pair. The shading shows it can either be the vorticity tendency, which is exactly equal in this theoretical case to the vortex stretching term, the minus FD term. Okay, this is the only source term. And the key thing is we have red shading, which is a positive vorticity tendency to the east of a positive vorticity center. So that means that with time, the whole structure will propagate to the east. So the forcing is a quarter wavelength out of phase with the actual perturbation. So that's the key thing to look for propagation. So now let's move on to the actual observed CCKW structure. I'm just going to look at the lower troposphere, 850 hectopascals in this talk, using I've done lag composites of era interim data that have been wave number frequency filtered. Again, we've got lag -1 day, 0 day, and +1 day, and you can see that the whole structure propagates eastward at about 10 meters per second. If we look in detail at the dynamical structure, the vectors here show the wind field, and again you can see that it's approximately a maximum on the equator, and it does decay north and south, and it does actually have an approximate Gaussian structure. If you look at the vectors, they're all pointing either towards the east here or to the west there. There's very little V wind. So in this sense, the dynamical structure is very similar to a theoretical equatorial Kelvin wave. Associated with that wind field, we have a cyclonic vorticity pair, just as with the equatorial Kelvin wave. And again, we have convergence to the east of that. So it looks pretty similar so far. So if we now go on and actually construct the vorticity budget, the top panel, okay, so in each panel, the line contours are the same. And again, the line contours show the vorticity anomaly at lag 0. And again, we've got a cyclonic vorticity pair, so positive to the north of the equator and negative to the south of the equator. The top panel, the shading, shows the vorticity tendency, so that's d zeta by dt on the left-hand side of the vorticity equation. And you can see that you've got a positive vorticity tendency to the east of the positive vorticity. So that's going to give you eastward propagation. So that's the tendency. What about the source terms? Well, there in the second panel, basically the map of the source terms looks very like the map of the vorticity tendency. Well, that's a good thing. That means that we've got a pretty good closure of the vorticity budget. And that's confirmed by the bottom panel, which is basically the difference between the top two, which is the residual, and it's relatively small compared to these maps here. So now let's go on and look at each individual vorticity source term. So all those terms on the right-hand side of the vorticity equation. So there's a lot here. Again, the line contours between each panel are the same. They are showing the vorticity perturbation, and the shading shows the tendency from the vorticity source, the relevant vorticity source, a different one in each panel. So there's 8 of them here. Let's start with the minus FD term, the vortex stretching, that of course is the sole vorticity source for equatorial Kelvin waves. So that's this one down here. Now, first of all, we can see, okay, there is a source, but it's relatively small amplitude compared to the shading in some of the other panels. So it's clearly not the only thing that's happening. But it is roughly in quadrature with the vorticity anomaly. So the red shading is to the east of the red line contours. So that is going to lead to eastward propagation. But clearly, so if this was an equatorial Kelvin wave, all of these other source terms would be 0. There'd be no shading in them, but clearly that's not the case. So let's look at the terms, each of the terms. Here's the vortex stretching minus zeta d. So this is the divergence interacting with the relative vorticity, not just the planetary vorticity. And you can see this has got large amplitude compared to the minus FD term. And crucially, the red shading now is not to the east of the red line contours, the vorticity anomaly, it's in phase with it. So that's going to lead to growth. You've got a positive tendency where you've already got vorticity. So this term is going to lead to growth. We've now got the advection terms, zonal advection and meridional advection. Again, if you look at the phasing here, the zonal advection does lead to eastward propagation. We've got this red shading to the east, the vorticity anomaly, but we've also got a large area of blue negative vorticity tendency that's partly in phase with the positive vorticity, so that's going to lead to negative growth or decay. And similarly, the meridional advection term, we've got a strong positive tendency here where we've actually got a negative vorticity anomaly, so that's going to lead to decay. Vertical advection, as expected at this level, is weak but non-zero, and that leads to growth. The tilting terms, one of them is basically zero, the other one is again non-zero and leads to decay, and then the advection of planetary vorticity, the minus beta v term, is very weak. So overall we've got a much more complex mechanism here than just an equatorial Kelvin wave. We can summarize these in these bar charts. So each bar corresponds to an individual term in the vorticity equation. So I've got things like the root mean square amplitude of each of the terms, spatial correlation coefficients, entropy generation. This tells you about which terms contribute to growth, which to decay, and then also the phase difference, okay, the fraction of a cycle between the source term and the vorticity pattern. And actually, I think I'll jump straight to the next slide now, because I'm basically going to show the amplitude and this phase difference on a polar plot. So I've called this a propagation growth polar diagram. Okay, so just to orient you here, I've plotted each vorticity source term. The radial coordinate is the root mean square amplitude, the size of that term, and the angle that it's at comes from the phase difference, the shifting between the source term and the vorticity anomaly. And it's all contrived such that if it's over in this quadrant here, that's going to correspond, the source term will give you eastward propagation. Over here will give you westward propagation. Up here will give you growth. And down here will give you decay. So this is quite a neat way of visually showing what all the terms do. So the vorticity tendency lies, all the terms are normalized with respect to the vorticity tendency, so that lies over here, and it gives you eastward propagation, as you might expect. And as a reminder, you can't see it very well actually, but there's a grey square there that says EKW. The theoretical Kelvin wave would lie exactly here as well, okay, both the vorticity tendency and the minus FD term, because the theoretical K wave propagates eastward and has no growth or decay. So where do all the source terms for the CCKW lie? Well, here's the minus FD term for the CCKW, okay? It's not over here. It does give you eastward propagation, it's just about in the blue sector, but it also gives you a bit of growth as well. We also get growth from this is a mixture of growth and decay from the zonal advection. And when we look at the main growth terms, the main one is the minus C to D, vortex stretching. Okay, that gives you strong growth. Also, here's the vertical advection term, also giving you rather weaker growth. These are countered, so some terms give you growth, some other terms give you decay. So the zonal advection, as we've talked about, also the meridional advection, and one of the tilting terms. When you add up all of those sources together, you get the total source term, which is this purple dot labeled S here, and you can see that the total source gives you eastward propagation, but also slight growth. Okay, so that's overall what's happening to the CCKW. So overall, we can maybe still think of the CCKW propagation and growth as being somewhat like a highly modified theoretical wave, because the minus FD term is still the main term that gives us eastward propagation, but clearly there are many other terms contributing. So to conclude, CCKW propagation growth is very much controlled by the lower tropospheric structure that I showed you here at 850 hectopascals, and the vorticity balance is that of a modified theoretical equatorial Kelvin wave. The upper troposphere, which I didn't have time to show, arises as a forced response to the lower troposphere. And the applications of this is that forecasting of CCKWs in numerical weather prediction and simulation and climate models will depend on the correct propagation growth mechanisms and vorticity balance. So this is a nice way of diagnosing that. So there's plenty more work to do here. I plan to incorporate the thermodynamical balance into this model and also moisture balance, apply to other locations, and apply, as I said, apply this process-based diagnostic analysis to NWP and climate model output to understand the errors there. And of course, this technique can also be applied to other phenomena, other equatorial waves and the MJO. So thank you very much for your time.